Hello there. So we're going to talk about vectors. Presumably you have some background in vectors, which is why this is called Vectors 2. And as you know, um, vectors have a magnitude and a direction. So there's two parameters you need in order to define a vector. You can also define it in terms of the x and y, for example. So we have here the indication of a two-dimensional vector that goes over 2 and up 7, whatever the arbitrary units are of this one. So we've got two ways of, so we've got either these two parameters or these two parameters that will give us the vector that we're talking about. I should be clear here before we go on that this vector that we're looking at starts at the origin, right, and it goes up to 2, 7. It would be the same vector if it started here and went up 7 and over 2. As long as this is true, we have the same vector whether or not it's in the same place. So, oops, that's actually not quite long enough. Let's make it a little bigger. There we go. So that's the same vector, whether it is there, or anywhere else. All right. So now that we have this vector, I've just shown it to be starting at the origin here because I think that's, well, it's a little bit easier to deal with when it starts at the origin. So now the question that's posed on this handout is, what is the magnitude of the vector? And I'm sure you know how to solve that. So the magnitude, we'll call this vector v. And the magnitude of vector v is given by the square root of the v sub x squared plus v sub y squared. So let's go ahead and figure out what that is. That is the square root of 4 plus 49. And that's equal to the square root of 53. And I don't really care what the actual decimal number is for that. Did I do that math right? Hope so. Okay, moving on. Oh yeah, I did. Okay, so now that's the magnitude of the vector. And we said there's two parts. We have the magnitude and the direction. So let's take a look at what's the direction. We can think of the direction as being a point on the unit circle. So in this case, we've drawn a unit circle around the origin, around the beginning of the vector. And we look at where the vector crosses the unit circle. And that's this point right here. Make it bigger. And that point is given by the coordinate. Well, we know we'd go just dividing each of the magnitudes, the x and y magnitudes, by the overall magnitude to find out where it crosses. So it's going to cross that unit circle at the point that's given there as, as 2 over the square root of 53 in the x direction and 7 over the square root of 53 in the y direction. So we've got a little vector here that has length 1, and it goes over 2 over the square root of 53 and goes up 7 over the square root of 53. And it has length 1 by definition. So it implies that we can also express that direction as trigonometric functions. Well, so we'll take this angle here. This angle is theta, and theta is going to equal the arctan of 7 over 2. and the x component of that vector, of the unit vector, is going to be cosine theta, and the y component is going to be sine theta. So we could say that, or being even more ridiculous, we could say cosine of arctan of 7/2, comma, oops, I need another parentheses here, maybe I don't, and then sine of arctan of 7/2. Okay, enough absurdity. All right, so which brings us to the point of, well, what is our notation for a vector? There's lots of them out there. We're going to just explore a few. We're always going to indicate that the vector, I called it V, we're going to call it R, and we put an arrow over the top of it to indicate that this is a vector. A vector is a mathematical thing. It's like a number. A number is also a mathematical thing, but a vector is not a number. It has two parts that make it. Sometimes textbooks use bold to indicate vectors like this. I find that annoying. I prefer to always put the little arrow over the top of it, like I've been doing, so I would do that, over that. The magnitude of the vector can be designated as I did before, saying that you have these two vertical bars on either side. You could say that this is the magnitude of the vector, but my math colleagues here insist that when you're dealing with a vector, you do something different. And so we use the two bars on either side to indicate the magnitude of a vector. Even more commonly, I will simply write the magnitude of the vector is simply V. So that, or take the letter, so you strip off the arrow on top, and that indicates that you're talking about the magnitude of that vector. You see it most often in intro kinematics, something like A, and then, but usually we'll use the A in an equation that looks like, x equals x naught plus v naught t plus 1/2 at squared. What this is indicating is, in fact, the magnitude of the vector in probably the x direction. And we know it's in the x direction because we've got these x's over here. So that this A here is a magnitude of a vector. Let me erase all that. Goes away. Go away. Go away. All right. Usually we describe vectors by giving the coordinates of the endpoint if it were sitting on the origin, like we did here on the first page. We said that this is the vector right here that we're dealing with. But you have to remember that, like I said before, the vector is the same vector whether it starts at the origin or whether it exists somewhere in space. In modern physics, we talk a lot about vector fields, and that is a situation where every single point in space has a vector associated with it. And they can be slightly different from one another. They're all different vectors. And every point has its own vector. You can think of that kind of like if you were in a windy area, different places would have different amounts of wind, both in magnitude and direction, as the wind goes around a corner, say. So every point in space has a vector, and this is what we call a vector field. Right, and you can take any one of these. Let me grab this one, for example. Oops, try that again. Take this one, and we can move it to the origin, and let go. And then where the tip of that vector ended up, I'm put a big red dot there. That is the coordinate that we would then put into this kind of notation here that we are about to deal with. So there's a few different kinds of vectors. This is a very, this first one that I just highlighted is a very linear algebra kind of vector. It's indicated with two values, one on top of the other. This is also a linear algebra one. They're both valid. Yeah, let's leave it at that. You can indicate it with this ordered pair type notation. And even though I did it on the very first page over here, I recommend not using this notation because this is ambiguous. Because it could be looked at as an ordered pair, and we want to indicate that it really is a vector. So we want to use something that is specifically designed for vectors. So this is preferable. This is known as bracket notation, and we can get into later when we get into quantum mechanics. We're going to use these a little bit differently, where you actually have the first component of the vector, and the second component of the vector would be put in here and in here. We call that the bra and the ket. Excuse me. But anyway, this is a valid vector notation, one that I kind of like. You can simply say that the x component of the r vector is 2 and the y component of the vector is 7. I really like this sort of notation here, specifically the first one, where we say that the I hat vector is a unit vector. I hat is a unit vector, meaning that it has length 1, in the x direction, the positive x direction. And the j hat is defined, oops, that should be a hat, is defined as the unit vector in the y direction, positive y direction. So now, when you multiply 2 times I hat, you get a vector that goes over to the right 2, and then we add to that 7j hat, and we get a vector that goes up 7. Add the two together, and you get the original vector that we've been talking about. So here's our vector. I will draw in red. I'll show you the 2x hat. And this is 7y hat. You add the two together, and you get this vector that we started out with and that we want to accomplish. So I really like this because it is explicit algebraically that this value here is in fact a vector in all components. Here that's slightly ambiguous, and I won't even talk about the linear algebra thing because they think about vectors in a different kind of philosophy. They're less physical things and more mathematical objects. You can also replace the I hat and j hat with x hat and y hat. I know a lot of people prefer this, and there's good reasons to do either one. I find, so sometimes you'll get like the magnitude in the x direction times the x hat vector gives you something like that, and I find that a little bit confusing. And you say x hat, yeah. So I like to say instead x I hat. But okay, that's a matter of taste. Oops, there it is erasing. Okay, good. Okay, and I just talked about all that. All right, so generally it looks like this, right, where we have the vector r is given by the magnitude in the x direction times x hat plus the magnitude in the y direction times y hat, and that gives you a vector that looks like that. This is similar to what you may have seen for complex numbers. It's not the same. I want you to be really clear that this is a complex number, which is also a mathematical thing, but it is not a vector. Because you can actually have a vector of two complex numbers. Yeah, so that gets a little weird. That happens more when you start getting into deeper physics, stuff that you can't immediately intuit. But it's possible to have Ry, for example, be a complex number. What does that mean? It's not really clear. but the point is that you're familiar with this kind of ability to add two things together to get something new. So in the complex plane, it looks like a vector. So this is going to be, this is the x direction. This is the imaginary. All right, okay, that's right the first time. This is a real number value here. That's the real direction, and up there is the I direction. And if we have this point here, then you're going to be A over and B up. So that's this number, this point is A plus BI. It's not this vector. That's a little different. Even though we'll often draw that vector just to be able to figure out what's going on. Draw that thing that looks like a vector, I should say. Alrighty, I hope I didn't confuse you too much with that. So, like I started off on the first page saying that the direction of the r vector is given by r hat. And we put the hat over the r to indicate a vector direction. It has length 1. This is useful because now I can say that the vector r, let's draw that with an arrow over it, equals the magnitude of r times the direction of r. We've got pieces that we can take out from one another. Because this has length 1, we know that if we multiply it times this magnitude, we will end up with a vector of the proper magnitude. Okay, so you're multiplying by 1. Or you're multiplying by a kind of 1. 1 of that vector. So let's take a look back to our first example. So this r hat vector we said was 2 over the square root of 53 in the x direction and 7 over the square root of 53 in the y direction. And we end up with this r hat, if we work out the length of that, so the magnitude of r hat is given by the square root of 2 over square root of 53 squared plus 7 divided by the square root of 53 squared. Boy, this is getting complicated. So what do we have here? Working offline, error occurred. I wonder what that means. Let that go away. So we'll have the square root of 4 over 53 plus 49 over 53. And that equals, I'm running into the other stuff, I'm going to have to delete this later. That gives us the square root of 53 over 53, which equals 1. So good, the magnitude of this is 1, which is what we were hoping for a unit vector. Gosh, I hope this is okay. You can always pause this video and go back. I know I'm going kind of fast. I'm not trying to go slowly because I know you have the ability to control the speed of a video. Here's a thought-provoking question. Components of the unit vectors are always between what and what? Pause your video for a moment and come up with the answer for that. And then when you get back, hopefully we'll have the answer. Pausing. And yeah, you're back. So the components of these unit vectors, I think you might have said they're between 0 and 1. That's a reasonable guess. It's not right. The correct answer is that these unit vectors are always between -1 and 1. Explain to yourself why that's true. Okay. So here, the x component of the unit vector, r sub x, is less than 0, right? So it can go out as far as -1 if the vector goes straight over that way. Cool, -1 and 1. Consider the point on the unit circle given by the angle 5 pi over 6. So if we have a unit circle... Uh-oh, what just happened here? Screen went black. It went away. Connecting. You've got to be kidding me.